In this video, we're going to look at two different types of titration calculations. The first one will be hydrochloric acid with sodium hydroxide, a strong acid with a strong base. And the second example that I'll do is acetic acid with sodium hydroxide, a weak acid with a strong base. So in this first problem, we're given a volume and molarity of hydrochloric acid and a molarity of sodium hydroxide, and we're asked to calculate the pH at the equivalence point. To solve a problem like this, we're going to take 4 steps. The first step is to think about what the equation looks like when hydrochloric acid reacts with sodium hydroxide. We're going to calculate how much sodium hydroxide and NaHCl we have initially, and figure out how much product we make, and then we'll figure out the pH of that product. So first of all, one at a time, the equation for this reaction looks like this: HCl plus NaOH reacting in a 1-to-1 ratio to make sodium chloride and water. To calculate how much we have initially of hydrochloric acid, we are going to use the volume and the molarity that's given to us. And here's the molarity multiplied by the volume, and that tells us how many moles of HCl we have. For the sodium hydroxide, we're given a molarity, but we're not specifically given a particular volume of sodium hydroxide. However, we are told that we're doing this calculation at the equivalence point of the titration. By definition, the equivalence point is when we have the same number of moles of both of our reactants. So at the equivalence point, we will have 0.002 moles of NaOH. So we don't even have to do any calculations to figure that out. We just know that because it tells us we're at the equivalent point. So once we know our initial amounts of hydrochloric acid and sodium hydroxide, we can set up an ice table to figure out how much stuff we're going to make. Because this is a forward reaction, strong acid with a strong base, and not in equilibrium, we know that all of the hydrochloric acid and NaOH will react, leaving us with nothing, and we can use our stoichiometric coefficients to figure out how much NaCl and H2O will be making. So we have that in moles. Then the last thing we want to consider is what the pH is of this solution. So when this titration is done, or when this titration is at the equivalence point, in our flask we have some sodium chloride and some water. In order to figure out the pH, we just need to think about the acidity and basicity of both of these products. Sodium chloride is a neutral salt. It is a group 1 cation, and chloride ion, which is a neutral anion. So it in itself does not have any acidic or basic properties. Water also is neutral, so the pH of this solution at the equivalence point is just 7. And that's going to be true anytime you titrate a strong acid with a strong base. Always. At the equivalence point, the pH is going to be 7. So we kind of didn't need to go through these calculations at all. By definition, the equivalence point of a titration between a strong acid and a strong base will always have a pH of 7, and you don't need to do the math. That is not the case when you're doing a titration between a weak acid and a strong base. So if we have a problem like this, a volume and molarity of acetic acid, CH3COOH, with a strong base, sodium hydroxide. The equivalence point of this titration still is going to be when we have the same number of moles of both acetic acid and sodium hydroxide, but the products of this reaction will not be neutral, and so we will have a pH that is not equal to 7 at the equivalence point. There are more steps involved to solving this type of problem, and it looks like this. The first thing that we're going to do is write out the equation for the reaction, and we're just going to double check and make sure that the products of the reaction are not neutral. That way we won't accidentally go through a bunch of steps like we did in the last example. And we'll find in this case that the products are not neutral. When the products are not neutral, we want to figure out how much reactant we're starting with, how much acetic acid do we have, how much sodium hydroxide do we have, and then we're going to set up an ice table to figure out how much of our product we make in moles. We're then going to figure out what the concentration is of our product in molarity. We're going to think, because our product is not neutral, we're going to think about how it reacts with water. Does it produce H3O plus or does it produce OH minus? And we're going to calculate exactly how much H3O plus or OH minus is produced in this reaction with water. And then we'll figure out from that what the pH is of the solution. So first of all, this is what the equation looks like when acetic acid reacts with sodium hydroxide. The products are sodium acetate and water. This is a basic salt. The sodium ion is a neutral cation, but the acetate ion is not. It's not neutral, it is basic. So the pH at the equivalence point is not going to be 7. And our second step is to figure out how much reactant we start with. And we're going to use the same method that we used for the strong acid, strong base titration. We're going to use the molarity of the acetic acid multiplied by the volume of acetic acid that we're using. And that gives us the moles of acetic acid. And remember, again, by definition, because we're talking about the equivalence point, the moles of acetic acid will be equal to the moles of sodium hydroxide. That's what it means to be at the equivalence point. So once we have that starting information, we can set up an ice table, which will look like this. We're taking our initial moles of acetic acid and sodium hydroxide. This is a forward arrow, so they're both going to be reacting to completion all the way, leaving us with nothing. That amount is how much we're making of both of our products. The water really doesn't matter, as we've talked about in class, because it's not part of any calculations that we do. What really matters is this stuff over here. Notice that this ice table is being done in moles, not in molarity. And that is because in a titration where you're mixing things together, the volume is changing, so the concentrations are changing as well. And that's why we need to do this ice table in moles and not in molarities. And that leads us to the next step of 4, which is to figure out exactly what the molarity is at the end of the titration. The molarity we really want to calculate for the sodium acetate. Remember, by definition, that is the moles of sodium acetate per liter of solution. The moles of sodium acetate are 0.002, which we just figured out. The volume of the solution is the 10 mils of sodium hydroxide, or 10 mils of acetic acid that we started with initially, at the beginning of the problem, and some unknown amount of sodium hydroxide. We've added sodium hydroxide, we just don't know exactly how much we've added at this point. We do know that we have added 0.002 moles of sodium hydroxide, and we can use that information and the molarity of the sodium hydroxide to figure out the volume of sodium hydroxide that was added. So this is the amount of moles of sodium hydroxide that we calculated based on the number of moles of acetic acid. This is the molarity of sodium hydroxide that's just being used as a conversion factor. The sodium hydroxide's molarity is 0.3 molar, and so this is just upside down. Letting the moles of sodium hydroxide cancel, we're left with 0.0067 liters, which is roughly 7 milliliters. And so our volume, our total volume of solution, is the 10 milliliters that we started with, plus the 7 milliliters that we added. And here is our concentration calculation, our moles of sodium acetate, 0.002, divided by our volume of solution in liters, 0.017. And there's our molarity. So the next thing that we need to think about is how the sodium acetate reacts with water. So first we're going to set up an equation to show us what the products are, and I'm showing you that sodium acetate reacts with water in an acid-base reaction to produce acetic acid and sodium hydroxide, which is what we started with. So we're just kind of putting it back, which makes sense if you understand the concept of equilibrium. We're going to make an ice table for this reaction because ultimately we want to be able to calculate the concentration of the sodium hydroxide. That's what's dictating the pH of the solution. So we're taking the 12 molar sodium acetate that we just calculated, and we have initially no acetic acid or sodium hydroxide. They were reacted all the way down to nothing, which we calculated in this ice table in step 3. Because this is an equilibrium reaction, we don't know exactly how much of the sodium acetate is reacting, so we're going to use X here, minus X. And we're going to be adding X, sodium hydroxide, and acetic acid to the products. We're going to make the assumption that X is very small, so at equilibrium we're still going to have about 12 molar sodium acetate and some unknown amount of acetic acid and sodium hydroxide. We can set up an equilibrium expression for this reaction, products over reactants raised to their coefficients. Remember, we're leaving out water because it's a pure liquid. I am telling you that the equilibrium constant for this reaction is 5.6 times 10 to the minus 10. And we're plugging in X for acetic acid and sodium hydroxide, and 0.12 for the concentration of sodium acetate. And then we're just doing the math to solve for X. X is the concentration of sodium hydroxide, which is the concentration of hydroxide, as we've discussed in class. Now that we know the concentration of hydroxide, we can figure out the H3O plus concentration using the Kw equilibrium expression for water. Kw is H plus times OH minus. We're going to rearrange this equation, plug in the value of Kw, plug in what we've calculated for OH minus, and there is our H plus concentration, which we can then plug in to calculate the pH of the solution. And that is all there is to it.